All right, so today we're going to continue with trees and tree-based data structures. We've covered pretty much all the things that we wanted to cover with binary search trees. So we're going to talk about the data structure that you were implemented or that you were exposed to in your lab yesterday, if you chose to do the lab, heaps. All right, and the motivation here is that binary search trees are not necessarily balanced, right? We started this entire discussion on trees and tree-based data structures with the desire to have an efficient collection data structure that you could put stuff in, take stuff out, and remove stuff all efficiently. And we looked to trees because trees, if they were full, they had a depth that was logarithmic. So we were able to achieve the efficiency of binary search potentially with all of those operations proportional to the depth. But we've already seen that that's not necessarily the case, right? We've already seen trees where you can have a skew, right? We call those linked lists, right? And you can have a depth D that is order n. No better than a linked list for all of your operations, right? Now, the real solution that goes beyond the scope of this course is to rebalance a tree. And these are called balanced binary search trees. And there are at least a dozen different implementations of these. I'll show you one idea, right? So suppose that your tree gets too skewed to the left, right? That is not a balanced binary search tree because everything is to the left, right? In fact, let me give these names, right? So C, B, A, right? And it's in lexicographic order. Now that's a binary search tree, certainly, but it's all skewed all completely to the left. So what you can do here is you can imagine that there's a hill, right? And on that hill, what you'll do is you'll take this and you'll pull it down over the other side of the hill. And eventually you'll end up with this is called a right rotation. You'll end up with B at the top, A still hanging off as the left child of B, and then C now hanging as a right child instead of the original parent. And guess what? You've balanced the tree, right? And there are various ways that you can do this. There are other types of trees that guarantee a logarithmic depth, but we won't get into that. Instead, we'll get into a different data structure that has the same guarantee, but with other conditions attached to it. So again, BSTs in general may have D being order n, which kills efficiency on all of the operations, right? All of the operations, right? The solution ultimately is to have what are called balanced binary search trees, BSTs for short. For example, AVL trees. The AVL just stands for the author's names, the three people that designed them. There are 2-3 trees, or in general, there are things called B trees. Those are actually what are used in a lot of database implementations. Red-black trees, right? All of these do some sort of a rebalancing to guarantee that the depth is going to be logarithmic. Each guaranteeing that, is that how you spell it? Yeah. That the depth is going to be order log n. I'll write it like this. There we go. Does that look nice? Nice enough. There we go. All right, so we don't have that guarantee with binary search trees. But I'm going to show you another tree-based data structure where we do have that guarantee. All right, a heap. Right, it's not like it's kind of like a heap in memory versus a stack, but it's not exactly like that. Right, a heap is a binary tree that has the following properties. One, it is full. One, it is full. Right? This is called the fullness property. Every child is present at every level except possibly the last one, which is full to the left. Right? And what do I mean by that? I'll draw you a picture here, both abstractly and an actual example. Right? It also satisfies the heap property. It satisfies the heap property. This is what makes it not a binary search tree. Every key value, every node, I can't type today, sorry. every key node value is less than both of its children. Right? In other words, this is called a min heap, right? And we'll see why here in a second. Okay, those are the two properties that a heap is going to satisfy. Now, pictorially here or visually, what does it mean to be full? It means that everything is present, right? You have every single child here. You have every node has both exactly two children, except possibly the last row. And if the last row is not full, it is at least full to the left. I wrote left, right? Instead of right? Yeah, okay. So in other words, everything is full up until this second to last level. And then at the last level, you have all the children, but they're all the way to the left. They're all contiguous, right? You don't have any gaps, right? For example, here is a binary tree, right? And we'll have it like that. Right? That is not a heap because it does not satisfy the fullness property. There is a gap right here, right? However, if I made that a left child instead, then that is a heap. Well, not necessarily a heap, but it satisfies the fullness property. Right? Now, if you have every node all the way up to the last level, then of course that's still full as well. Right? Now, what does this fullness property guarantee? It guarantees that the depth is going to be logarithmic because it's full. Right? Now, what does it mean for the heap property? It means that if I've got a key here, K, then if I look at both of its children, this is L and R, I have a guarantee that L is the left child is going to be greater than K, and the right child is going to be greater than K. Now, does that look like a binary search tree to you? No. Right? In fact, it would look like something like this. If I have 20 at the root here, then could I have 10 here? Nope. That would have to be necessarily larger, right? And 25 over here. That is certainly not a binary search tree, right? Because there is something larger on both sides, okay? All right, well, let's again read the heap property here. It's every key node value is less than both of its children. So where does that tell you where the minimum element is? It's at the very top, at the root. Right? Let's take a look at a full example that I've already prepared here. Where is it? Min heap. There we go. There's a min heap, right? It satisfies the fullness property. Every single node is there all the way up to the second to last level. And at the last level, they're all full to the left. Right? It would not be the case where we have something hanging over here or something hanging over here, because then there would be this huge gap in here. Okay? It also satisfies the min heap property, because if you take a look at any node, it is less than both of its children. Another node here, 50, it is less than both of its children. Right? So it's an inductive property that holds for every single node. So we lose some of the benefits of a binary search tree here. If I wanted to search for 65, right? If I started at the root here, would I know which way to go? Nope. It could be over here, or it could be over here, because 65 is greater than 1. If I were searching for 1, then I'm done, right? But if I'm searching for a particular element, basically I'm stuck. I'm going to have to do a full pre-order traversal, in-order traversal, post-order traversal, or whatever. And the in-order traversal in this case is not, because it's not a binary search tree, is not going to give me an ordered list. Okay? But what do we have the advantage here? What are our advantages that we do have with this data structure? The fullness property guarantees that the depth is going to be logarithmic. So if we can come up with some operations that are proportional to the depth still, then we still have a little bit of a win, because it's all going to be logarithmic. What other property do we have? The min heap property. What does that give us access to for free without any complicated algorithms or anything? The minimum. Right? And so those are going that's going to be one of our basic operations here, right? So they're the fullness fullness property guarantees that the depth is logarithmic. Right? We're not going to have, it is not a general access data structure, like a list or a binary search tree or something like that. Instead, it is a restricted access data structure. We've looked at two restricted access data structures before, stacks and queues. Their efficiency derived from the fact that you were only allowed to access things in a certain way. The same thing is going to happen here. We're not going to be allowed to access arbitrary elements. If you want that, then you need to shop for a different data structure. Instead, you're only going to be able to get and remove the minimum element. And then you can put stuff in, right? You can add elements to the heap. Right? Those are going to be our two basic operations that we want to focus on. If you want a general access data structure where you're searching for anything, where you maybe have some more control on where you put something, that there's an ordering or something like that, then you need to shop for a different data structure. Both of these operations are going to be guaranteed to be proportional to the depth of the tree, or the depth of the heap, and therefore they're going to be logarithmic as well. Right? So how do we go about taking care of these things, or implementing these things, first of all? All right, well, let's come over here. And let's think about getting the minimum, getting and removing the minimum here. Right? Well, getting the minimum is no problem. It's right there. But if I wanted to remove it, how would you go about doing it? Well, it's gone, right? I saved it off. I saved off, oops, it was 1, right? Right. So I saved it off to return that value eventually. But now I've got, is this a heap anymore? Nope. There's a gap, right? So what could we do? What's one potential thing that we could do? We could promote up the minimum child, right? By the way, this is a min heap because of the heap property. You can go ahead and flip that around and have a max heap where you've got the maximum at the top instead. Really doesn't matter because in practice you'd be doing this with a comparator. And if you have one heap implementation that's a min heap, if you want it reversed, you just give it a comparator that reverses everything. Right? So there's only going to be one implementation here of a min heap. So let's go ahead and promote up the minimum child here. I don't like that thick none. There we go. 5. Right. Well, what does that do for 5? Right. Now there's a gap. So we have to continue to fix this thing. What's the minimum that you would put up now? 50, okay. Oops. 50. And then now you have a gap here. So which one would you promote up? 53, because you need to be consistent about it. And guess what? Are there any children left to promote up? Nope. That didn't work. Let's go back. All right. So I will go ahead and save it off for later to return it eventually. But I've got this gap here. We tried to satisfy the heap property first by promoting one of its two children, right? Let's go the other direction, and let's try to satisfy the other property first, the fullness property. All right? Now, to satisfy the fullness property, that means that I'm going to go to the very last node at the deepest level, all the way to the right, and that's what I'm going to promote up here. Let's try that strategy instead. 63. Now, once I've got that, then of course I can delete this entire node. There we go. And it's completely gone. Now, is the fullness property satisfied? Yes. But is the heap property satisfied? No. Let's take care of that next by working with its two children. What could I do with 63, 5, and 30 in order to fix the heap at least at this level? Swap. Why did you go to 5? Because it's the minimum, right? I'll swap these. Okay. When I swap them, what does it look like? Thicker. There we go. 63. 63 goes down here. 63. And what was up here? What was it again?
5. Thank you. All right, well, that's satisfied now. The heap property is satisfied for everything at this level, right? But is it still a heap? Or is it a heap now? No. 63 is greater than both of its children. So what do I end up doing there? I swap. Right? And I'll just cross them out here. 50. And now 63 is down here. Now is the heap property satisfied? Nope. What do? Swap it with its minimum child. Right? So 63 goes down here. And now 53 is up here. Right? And now is it a heap? Yep. So you promote the last child, or the last node, all the way to the top, saving this thing off so that you can return it. And then you fix the heap. We call that heapifying, or fix heap, or something like that, whatever you want to call it. By bubbling that child down until either it's where it needs to be, or you reach the end of the line and there are no children left. And then the heap property is then satisfied. So there is the get min operation. What about adding an element onto the heap? Right? So now think about this visually. Let me go over there. All right. Now I've reset it. Say that I want to add something to this heap. What about, say, adding 1 to it? Yeah, let's not let duplicates, right? If you have a good comparator, a good comparator will always be a total order. And so we won't allow duplicates. We won't worry about that. Okay. So what if I wanted to insert, say, I don't know, is 25 in there? No. Let's go with 25. Okay. I wanted to insert 25. Now, imagine this as a heap of garbage, right? That's where the term comes from. It's just a heap. It's a big old pile, not necessarily an organized pile, not necessarily a disorganized pile, but it's a pile of things. Now, where would you throw something onto a pile? At the top, right? And then you would let it, you let gravity take effect and it would go down to where it needs to be or something like that. If I did that, what would that look like? If I tried to throw 25 into here, right? I could start doing my tree traversal strategies, right? Of, okay, well, where does it need to go? Does it need to go to the left or the right? Do I shove out one, right, and do something with it? I don't know. Right? Unless you can view the entire tree and see that, oh, okay, it needs to go there, 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 and eventually there, then you're going to lose the forest for the tree, right? Literally. Right? There is no forest here, though. It's just a tree. Right? So maybe we don't start at the top. Instead, we throw it on the top, if you want to visualize it like that, but then it trickles all the way down to the bottom. Could I put a new node, say, as a right child of 70? That would not be a heap. There would be this gap here. So where would I want to put it? At the left child of 53. Now the fullness property is satisfied still. But is it a heap? Nope. All you need to do is the same trick, but instead of going top to bottom, you're going to go bottom to top, right? So 25 and 53, are those in order or out of order with respect to the heap property? Out of order, so swap. Right? 25 and 53. Now you look at its parent, 25 and 50. And are those in order? Nope. So 25 goes down to 50, and 25 comes up here. Now is the heap property satisfied? Yes. What if I were to insert 0? It would end up having to be bubbled up all the way to the top, replacing the original root, right? And guess what? If I were to insert 0, that's the minimum. Where should it be? At the root. Right? So the heap property preserves the fact that the minimum is at the top so that you can go back to your other operation of get and remove the minimum element. This is perfectly suited for a priority queue implementation, right? A heap is a nice implementation of a priority queue. What is a priority queue? It's a line, but you have very important people at the front, right? That the next person served
is the next is the one with the highest importance, not the one that came in last, right? Just a regular old queue is going to be a FIFO data structure. First in, first out, right? Everybody is equal. But a priority queue is, allows line jumpers, remember? Okay, I have a higher priority. Okay, you can come to the front of the line. I've got a priority greater than the people in the back of the line, but less than the people in the front of the line, so you go somewhere in the middle, right? To simulate that, you can use a heap. Why? Because you're always getting and removing the next minimum element. When you put something in, it doesn't matter that they're standing in a line or they're standing in a big pile of people. The next person to come out is going to be the one with the minimum value, the highest priority, right? So a heap is a very nice implementation of a priority queue, okay? How would we go about implementing this in an actual program? So let me go ahead and restore. Actually, no. Let me go ahead and erase all this stuff. All right. Think of this as an array. Right? Why think of this as an array? Because everything is full. It's also contiguous. Right? So in other words, write them all out in a line. 1, 5, 30, 50, 55, 40, ... I'm not going to write them all out again. What order is that? I start at the top and read it left to right, top to bottom. What order was that? Do you remember? Nope. In order would be going left subtree, then the root, then the right subtree. But reading it top to bottom, left to right, is a BFS, breadth first search, right? Why? Because you're exploring things that are 0 distance away, then exploring things that are 1 distance away, then 2 distance away, 3 distance away, and 4 distance away. Right? And so that's a BFS, breadth first search traversal on a tree, rooted tree. Okay. So I'm going to go ahead and list it in a BFS order. Right? Why does that help me? Think of this as an array. We're going to go ahead and burn the first one, the first index, 0, and then 1, 2, 3, 4, 5, 6, ... Right? I store everything contiguously. Is it in order? Is it sorted? Nope, that doesn't look sorted to me. 1, 5, 30, 55, 40, then goes down to 40, right? It looked all right for the first 5 of them, but then the 6th one, no, right? It is not sorted. But it is contiguous. And if it's contiguous, then we have random access, right? We can jump to any memory location in that entire thing. How can we simulate the fact that this is a tree, though? So let's look at the root right here. Where's its left child? Right next door. Where's its right child? Right next door, plus 1. Right? 450, right here, right? Where's its left child? Here, now I'm going to have to write the rest of them out. Thought I could get away with it, but all right. So 7, 8, 9, 10, and that's going to be 40, 80, 60, and 53, and 72, ... All right. All right, so back to this guy right here. 40. Where's its left child and where's its right child? Not next door, but somewhere over, and somewhere over, then plus 1 next door. So do we see a pattern here? What about 30? Where are its children? 40 and 50, 40 and 80? Somewhere over, and somewhere over plus 1. What was common about all these things? 1 goes to 2 and then 1 over. 4 goes to 8 and then 1 over. 3 goes to 6 and then 1 over. What's the pattern? Yeah, if I'm at index I, where are my 2 children? 2i and 2i plus 1. Right? And that's why we burn 0 here, just so that the math works out. Otherwise, you'll be subtracting 1 for everything, right?
Now, what about its parent? So if you can go one way, you should be able to go the other way. Right? Let's come back over here and look at the examples. Well, if I'm 8, where's my parent? Just reverse it, right? If I went from I to 2I, then to go back, 2I to I is going to be divide by 2, right? So it's going to be I divided by 2. Well, that doesn't necessarily work out for this guy right here. 9 divided by 2 is 4.5, and that ain't an index that I've ever heard of. But what can you do? Take the floor, or truncation, right, if it's an integer. Right? Take the floor. Let's see if that works. Right? Going from 7 back to 3. 7 divided by 2 is 3.5. 4 is going to be 3. 6 divided by 2, that works out perfectly. 2 divided by 2, that works out perfectly. 3 divided by 2, floor, is going to take us right back to 1. Very, very cool that you can do this with just a division by 2, multiplication by 2. And relying on truncation, then you don't even have to do a floor, right? That is so simple to do in code. How would you do that? How would you divide by 2? I is equal to I divided by 2. What's another way of doing that? I divided equals 2, sure. What's another way of doing that? Ooh, cool. What is that? That's a shift left by 1 bit. Sorry, that's multiplication by 2. Right? No, yeah, sorry. Divide by 2 should be this way. There we go. And multiply by 2, you can, of course, shift left. So I is equal to I times 2. You can, of course, use the compound assignment operator, or you can go with a shift by 1. I is equal to. I is equal to. There we go. So if you've never seen that before, that's fine. But it's a nice little trick. Because how does it work? So if I were base 10, which we all are here, right? 3, 1, 4, 8, 7, 2. Right? Multiplying by 10, do you even have to think about it? No, what do? You float the point over. Floating point numbers. Right? Scientific notation. Right? If you want to divide by 10, what do? You float it left, right? And that works because it's base 10. If you want to multiply by 10, divide by 10, all you have to do is move the decimal point over. In binary, we aren't base 10. We are base 2. So shifting things over by 1 or shifting things over by the other way corresponds to multiplication or division by 2 instead. And it's so common that they made a thing for it, right? They made a operation for it. It is the greater than or less than sign here. And it shifts things over by 1 bit. If you want to take a look at what that looks like, we're not base 10 anymore, right? Let's see. 7. 1, 1, 1, right? If I shifted that over by 1 bit, what would it become? 1, 1, 1, and then 0 comes in and fills in that location. Why? Because there's a point here and then 0, right? Implicitly. Okay. What value is that? No? Oh, we don't know binary? 230, 231 yet? Maybe not? Okay. So this is 1, 2, 4, 8. And so you sum these up. 2, 4, 8 is going to be 14. Wouldn't you know it? That's multiplication of 2 by 7. Right? All right, 7. 1, 1, 1. What if I went the other way? What if I shifted it over by 1? Right? And relied on truncation. What'll happen then? 1, 1, and then this 1 falls off. It gets lost. There is a cyclic shift. One more will do a cyclic shift, and then that 1 will come back onto the other side. Don't worry about that, though. Some languages don't even support it. But now we've got 1, 1, which is going to be 1, 2. So sum those up, and you have 3. And wouldn't you know it, 7 divided by 2 is 3.5. Truncation gives you 3. Nice little trick. If you want to get into these tricks, this entire thing is called bit twiddling. Bit twiddling, right? Or masking, right? You can go ahead and go with a single AND operator or a single OR operator, and then you have a bitwise operations on all of your stuff. And it's a nice little way of manipulating things at the binary level, at the bit level, to get what you want, right? In fact, if you were to write, whatever. If you were to write this actual code right here, I am 100% positive it would probably get compiled to just a bit shift, because it sees that you're trying to divide by 2, multiply by 2, and so it'll optimize it as just a bit shift, and that's it. Okay. All right. So there's a nice implementation of a heap. Here is your lab from yesterday, right? And I want to show you that that's exactly what they did, right? First of all, let's jump into the priority queue, the actual collection here. And how is it representing its elements? An object queue, what is that? It's an array, just like I said, right? The nice way of representing this is as an array. Now, they probably do not burn the first one here, but they will have the exact same kind of implementation. Let's see, can we see a multiplication by 2 here? I don't know. What is it, pull to get the minimum? Shift down comparable, shift down using comparator. Yep, I think it's shifting stuff. All right, it's not gonna be. Oh, there we go. Hey, there we go. That looks familiar. What are you doing? You're subtracting 1, so it looks like they don't burn that first one. And then they're cyclically shifting it over by 1. What is that doing? That is dividing by 2, right? Where's another shift? Find the other way. They don't do it. Oh, well. Anyway. I already ran this once. This is the test example that we gave you in that lab, where we've got elements 9, 4, 6, 2, 7, 8, 1, 3, and 5. And all I've done here is added the code that adds them all to this, adds everything from that list to this heap, and then I print it out. There's the heap. Now, is that sorted? Hopefully we agree that that's not sorted. So where are they getting that ordering? Well, let's use that ordering and reconstruct it using an actual, I'll go ahead and, come on. Okay. Come on. There we go. There we go. All right, let's reconstruct it as a tree visualization. Again, it's not actually a tree because there are no nodes here. It's just an array. They're just putting stuff in an array so that it's all contiguous. But if I were to read this out in a BFS order, top to bottom, left to right, what would the tree end up looking like? 1 at the top, then 3, 2, then 4, 7, 8, 6, and 9, and 5. Hey, what is that? A min heap. It's not a binary search tree, right? And so a priority queue, their implementation of a priority queue is an array-based heap. Now you might be asking yourself, well, okay, it looks like that looks good to implement it as an array. What if I really don't want to do that? What if I wanted to actually implement it as a tree? And you can do that, and the 2 basic operations are still going to be efficient. You just have to do a hell of a lot more math. And if you're interested in that, then read the chapter in the book on that. I walk you through the entire math of, basically you have to answer a question of, all right, well, starting at the root here, where's the next element here that I can insert? Is it in the left half of the tree or the right half of the tree? But because of the fullness property and because of the series, you can all you have to do is compute. As long as you've got the number of nodes there are, you can tell that the gap is on either on the left side or the right side. Then from once you make that decision, then you can ask the question again at a lower level. Is it on the left side or the right side? And then you can traverse down all the way until you get there, which is going to be order D, which is guaranteed to be logarithmic. Right. Okay. Great. Now that we've got our heap, what about one possible application of it? Right? You can use a heap to implement, as you did yesterday in your lab, a heap sort. Right? And this is actually going to be the culmination of everything in this course here, or at least one of the themes of this course that we started at the beginning with. A quote by Eric S. Raymond, that smart data structures and dumb code are a lot better than the other way around. Right? So how do you know how to sort something up till this point? What are some algorithms that you know? Selection sort. That's kind of a dumb algorithm, though. Inefficient algorithm. Insertion sort. Oh, clever, right? You don't. If you work from the other direction and insert stuff, then sometimes it's adaptive, and you don't have to make all of the comparisons. Right? Or quick sort and merge sort. Right? Those are divide and conquer strategies. Very, very clever code. Right? But what does your code look like for a priority queue here? Well, here was the outline I gave you. For each element X in the list, remove X from the list and add it to the heap. While the heap is not empty, remove the element, pull it, and add it to the list. Why does that work? If you take out the minimum element and then you put it in your list over here, 1, right? That removes that element. 5 comes up here, and then it gets trickled down. Where does it go? It goes over here. 5 and 2. 5 and 2. And now that's gone. Now you take 2 out, and you put it over here. And now that's gone. What does it get replaced by? 9. And now all of this stuff is gone over here. But you still have to fix the heap. And so it'll be swapped with that one, and then it will be swapped with that one. So what do you have? 3 comes up here. 4 comes up here. And then 9 comes down here. Right? Next would be 3, 4, 5, ... So you put stuff in, you take it out, and it's magically sorted. Right? Smart data structure. Dumb code. Dumb code as in you're just putting stuff in, taking stuff out, and that's it. All the magic happens under the hood in the data structure. Let's write out pseudocode to get more practice with pseudocode. Here's heap sort. Right? My input is going to be, just like we've done before, a collection, A, give it a name, A1 through AN, of integers, accounts, people, doubles, of elements. Right? Remember, it's pseudocode. Our output will be A sorted. There we go. So now take this outline here and just preserve it, basically, because that's pseudocode right there, right? So H, I will create a min heap. For each A, in A, H dot, and then add, right? Add, or NQ, or whatever you want. All right, add A, lowercase a there. Right? Now, while H is not empty, right, you can say that A sub I will then be H dot get min. Right? And then I plus plus, if you want to, just so that we have an index variable here. I is equal to 1. And then that's it. Output A. Dumb code, right? Just 2 for loops. Put stuff in, take stuff out. Put stuff in, take stuff out. But it's a smart data structure because of the structure that it gives you. It has a guarantee that as you pull stuff out, it's all going to be sorted. Right? It's not going to be sorted inside the data structure,
like a binary search tree is, but it's all, when it all comes out one by one, right, then it will be sorted. Heap sort. Now, this is a nice data structure, but it all falls apart if it's not efficient. Right? Remember, selection sort is inefficient. Insertion sort is slightly more efficient in practice, but it's still going to be an order n squared algorithm. Quicksort and merge sort, smart code, clever code, no data structures at all. Right? But they are efficient, order n log n. What is this one? Let's focus first on this phase right here, putting stuff in. Right? So put stuff in. Right? Here's the thing. The first thing, the second thing, the third thing, or iteration. Right? How many iterations am I going to do here for this for loop right here? Not n, just for each one in A, I will do this operation, right? So, for each iteration, for ... up to n. I'm also going to keep track of the size of the heap. Now, initially, how big is it? On the first iteration, is there anything in there yet? Nope. Is there anything in there on the second iteration? Yeah, I put the first one in. So 1, 2, ... On the last iteration, how many things are in there? n minus 1, and then you put the last thing in there. Okay? So, number of comparisons. Or swaps, or whatever you want to consider as your elementary operation. Remember, when you do this, this heap, right, you are when you are inserting something, you're putting it at the end, and then potentially going all the way back up to the beginning. So in other words, it's going to be always going to be order D, but we have a guarantee that D is going to be order log n, where n is the size of the heap at that moment. So in other words, the number of comparisons here is going to be log of 0. Can you have log of 0? Nope, that's undefined. But how many comparisons are you doing? 0, right? So for our purposes, it'll be 0. If you've ever seen Shannon's entropy function, they also say log 0, we'll just make that E0 to make it work, right? Do that all the time in calc too, right? It's defined everywhere. It's continuous everywhere, except for blows up at 0. Well, just ignore that. Right? It's still a continuous function now, right? All right, on the second iteration, how many comparisons do we do? Log 1. Right? On the third iteration, log 2, ... log n minus 1. So what is the grand total here? We'll go ahead and just forget about that one right there because it's 0 already. What is the grand total of all of these comparisons? Right? The total number of comparisons. Now, remember that we're only doing this for loop for now. Okay? We'll get to this here in a second. The total number of comparisons is going to be log of 1 plus log of 2 plus log of 3 plus ... plus log of n minus 1. Right? Log identities. Off to the side here. Log of A plus log of B is equal to log of A plus B. Right? Is that right? Now, what is it? Times. Close. Times B. All right? So what could I do with all these logs? 1 times 2 times 3 times 4 times ... n minus 1. Right? Okay. What is that thing in the inside there? 1 times 2 times 3 times 4 times 5 ... times n. There's a, we could write that with an exclamation point, right? What is that called? That's a factorial, right? N times n minus 1 times n minus 2. The number of permutations or number of arrangements of something, right? It'll be n minus 1 factorial, you're right. So I'll also be right. Right? It's less than or equal to. Remember, we're doing a big O analysis on this. So we make it bigger, that's okay. Make it bigger, that's okay. Right? Okay. Well, that factorial there, that's not that satisfying. Let's make it even bigger. Log n raised to the n. Now that's huge, right? So this is looking terrible, right? N to the n, factorial, that's huge. That's super exponential. N to the n is even bigger, right? Why is it even bigger? Because you can go ahead and replace each one of these terms with n. And you've got n times n times n times n times n. N times, right? And so this inequality still holds, but you have to remember what happens when you take a log. So another log identity. Log identity 2. Log a raised to the b is equal to b times log of a. Right? That exponent comes out front. And so this is equal to n log n. Right? Yeah, sure, the thing inside is huge. But when you take the log of something huge, it becomes something small. Right? Just like when you take a big number and you take the reciprocal, you get a really, really tiny number. Right? So we've got a n log n operation here, right? Putting n things into a heap is order n log n. Now, what about taking things out? That second phase right there. Guess what? It's exactly the same, but in reverse, right? Here, oops, oh, I don't know what I did there. There we go. To take out the first element will require potentially log n operations. Then log of n minus 1. Then log of n minus 2, dot, 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 until you get down to the bottom, and taking out one thing is only going to be 0 comparisons because you just have a root, a seed, you take it out, and there's nothing to compare to. Yeah. Right. So, putting things into n things into a heap is order log n. Taking n things out of a heap is order n log n. And now, are these nested? Nope. You do one, and then after you're done with that, you do the other. And so all combined, it's going to be 2n log n. But what do we do with that 2? We ignore it because big O analysis. It's going to be order n log n. So in one way, we've achieved the ultimate goal. We have a smart data structure and dumb code, but also efficiency. Right? If you're familiar with theta, this is also theta. Don't worry about that, though. Right? So, on one hand, you have dumb sorting algorithms and inefficient dumb sorting algorithms like selection sort. Then you've got clever code algorithms like merge sort and quick sort. And then you've got heap sort, smart code, or dumb code, smart data structure, and very, very efficient. So why isn't it always done like this? Don't ask me. There are other ways of there's tim sort and a couple of other merge sort variants and stuff like that. But heap sort is a very, very good algorithm to use, right? Especially if you have to roll your own, but you don't usually do that anyway. So that goes all the way back to the beginning, that smart data structures and dumb code are a lot better than the other way around. Of having really clever code and no or dumb data structures like an array or something like that. When we do our recap, probably on Thursday of this course, I'll bring that up again. Of one of the goals of this course at the end is instead of asking yourself, how do I do this problem, by breaking the problem down into smaller and smaller parts, you ask yourselves, what data structures would make this easy? What data structures could I just throw at this and it'd be solved, right? Could I throw a heap at it? Could I throw a stack in the mix? Could I throw a queue or whatever else, a binary search tree? And those are the questions you should ask yourself first. What kind of data structures would make this into a trivial problem to solve? Right? Because all the smartness is in the data structure itself. All right? Want to see it in action? I just added them all. Right? Basically, I did it all with cheating without doing a for loop here. Right? Why? Well, the for loop is inside that function, right? Inside that method. In fact, what does it look like? Huh. What does it look like? A for loop, right? There's my for loop while the heap is not empty. So while h dot is empty, while it is not empty, then I will need to say list dot add h dot poll. Right. There we go. Poll. There we go. And also, I'll probably want to clear the list out. Right. Dot remove all. Does it return it? Nope. Okay. So I'll remove all, but outside list dot. I think clear. Clear doesn't throw it either. Okay, fine. There. So I'm taking everything in the list and adding it all to the heap. While that heap is not empty, I just get the minimum element, and it turns out that it's going to end up being sorted. 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. I wonder does this allow duplicates? Let's put 2 9s in there. Probably does. Right. It just breaks ties arbitrarily. All right. I will not commit those changes. Any questions? No? All right, then. Well, since the in-person folks are the most affected, I'll give you guys the choice. We have, of course, Tuesday and Thursday next week. We could. I've got to be here no matter what. So really, we only have one wrap-up, the course wrap-up. And then we can do whatever we want. So I could do that on Tuesday, and then Thursday, no class. Or we could do something else on Tuesday and then do the wrap-up on Thursday. I have no idea what it would be. Multi-threaded programming. What else? I could show you JPA a little bit. I don't know, something like that. So basically just an extra topic. So do we want that or not? Extra topic on Tuesday? Okay, all right, fine. We'll go ahead and do that. Now you're making me work. All right, that means I'm gonna have to prep for it. I can show you JPA. Do I have a project with JPA? JPA demo. There we go. All right. So I'm lazy and I don't want to write any JDBC code. Now that I've learned how, I learn not to. Right? How do I do that? I use a ORM, an object relational mapping system. An object relational mapping system allows you to say, this object is associated with this table. This variable inside that object is associated with this column in that table. Right? And it automatically loads up everything. It automatically generates all the JDBC and SQL code needed to load that up from your database without you having to worry about it at all. Right? You title things with an entity. These are called annotations. You've seen them before, like override, you might have seen. But in any case, I'm associating it with the address table. Well, the address, it's going to have to generate these keys. How is it going to generate that keys? Auto-generated, right? And is it nullable or not? No, it cannot be null because I don't want nullable primary keys. How do I know that this is the primary key? There you go, right? There's a column street, ... Here's a person with an address. Oh, I didn't do that. Okay. How do you load things up? You have an entity manager factory. You have an XML file where you put your password and a bunch of other stuff. You create this entity manager,
And then you have very SQL-like code. This is called JPQL, Java Persistence Query Language, I think it is, right? And this address is not a table anymore, is it? It's a Java object. In fact, you can click on it and it'll take you to that Java object, right? So go back to the demo over here, right? How do you load things up? I just want to get all of the addresses, right? From address. Not if you want, you can say where address ID is equal to something. How do I do it? Question mark, I think, something like that, or 1. No, it's named. They're named parameters. So address ID. There we go. So you don't have to use the number system anymore. The ordinals of the first one is 1, the second one is 2, the third one is 3. You use a named parameter here so that it's not confusing anymore. We don't cover this directly because JPA is built on top of JDBC. So if you have, also you need to learn SQL. SQL, then you abstract that with JDBC. You abstract that further with JPA. It's also kind of a bear to use, right? You need a very, very clean mapping between your Java classes and your database tables. If you don't have a clean mapping, then you're going to be bending over backwards fighting this framework to get it to work. Right? We're going to ensure that it's a very clean mapping when I show it to you on Tuesday then. Right? Is it, you want to see this, or do you want to see multi-threaded programming? Yeah. Multi-threaded programming? Where you launch threads. Do I have any examples? So everything that you've been doing up to this point is a single thread, right? It means that if you, I have, I think, 12. No, this is an i9, so there are going to be, how many cores are there? 8? And then with hyperthreading, maybe 16 cores on my computer right here. No, if you look at your laptops, right? Do they say Duo? Like that means that there are at least 2 processors or that on the chip. Quad core, right? 4 with hyper. They don't call it Ocho, but they should, right? 8 cores, and then with hyperthreading, you can actually run 2 processes on each core at the same time, right? Here's a visual example. Let me pull up CSE. CSE, it's not a supercomputer by any means, but it's going to have 64 cores right there, right? 0 through 63. At any one time, this guy is using core 26 here, 100% of it, right? But over here, 21 is now idle at only 0.6%. And so all these things are being swapped out. Some cores are being used highly, other cores are not being used highly. Multi-threaded programming allows one program to grab multiple cores at the same time. So what you can do is you have one program that launches multiple threads, right? 8 threads, say, right? And each one of them are working in parallel. So that something that took, say, 8 minutes before, if you farm that out to 8 different processors, now it only takes 1 minute instead, right? Ideally, right? Now there are some things that you can't necessarily parallelize, but for all practical things that you'd care about, you can. And we can steal as many cores on CSE. We can try to do. I usually do that as a demonstration. It'll air out really quick because you're limited not by actual physical time. You're limited by CPU time. So if it only takes 1 minute, but you'd grab all 64 cores, it took you 64 computing minutes, and that ain't gonna fly. They're not gonna let me do that. All right, but we can grab like 8, 10 of them for a while. Whoever 27 is, they've grabbed it for a while. All right. So, JPA or multi-threaded programming in Java, of course. JPA? Okay. First one to speak gets it. All right, so we'll go ahead and take a look at JPA here. I'll have to make sure that this actually works and that it's set up to run properly. All right. We'll do that on Tuesday, and then we'll do the wrap-up on Thursday.
don't do JPA for your projects.